Hello everyone, welcome to another video. Today we're going to sort of introduce the topic of differentiation and where that comes from. So differentiation is like the original part of calculus. When I say original, the beginnings of calculus, where it all sort of come from. As a sort of like basic understanding of what we're sort of talking about when we talk about differentiation is if we have some function, um, some curve like that. Where we're sort of coming from is like, well, if you pick a point on the line, so I'll pick a point like say there, right? Let's say that point there. And so where this comes from is if I'm trying to find the gradient of that particular point there, how would I find the gradient at that exact point? And so when we have straight lines, the gradient is constant for the whole line. So that's the gradient's constant. It's easy to calculate. We can find from one point to the next point, we can find the gradient is y2 minus y1 over x2 minus x1. And we use that to find the gradient of the line. But what happens when we have a curve? And what we'll learn is that curve, the gradient at that exact point is like that tangent line there. Okay, so the essentially the gradient of that line of the tangent at that exact point. And what you'll learn is that if you've got the line of y equals fx, the gradient of that point, the gradient at the exact point is the derivative, the dy dx. And so what that means is that the change in y over the change in x, just like the gradient for a straight line is y2 minus y1 over x2 minus x1. That's the change in y over the change in x. Okay, how far has y moved divided by how much has x moved? And if we go down to the tiny change between that y and x, we call that dy dx. So d is the infinitesimally small change in y divided by an infinitesimally small change in x, and that will give us a very as the change gets smaller and smaller and smaller, it becomes more and more accurate, and d is infinitesimally small. So as the change approaches zero, then you get this exact calculation for what the gradient is equal to, and we call that dy dx. The other way we can write that is f dashed of x. So that dash there, or prime as Americans call it, f dashed of x there to say that's the derivative at the point, and that will give us the gradient of that. So if that was at the point 2, f dashed of 2 is the gradient at when x is equal to 2. Okay, and so that's how it all works, and that's what we're going to be talking about today. In the green box there, you'll see the derivative of any power function, so x to the power of something. So let's say if you've got f of x equal to x to the power 8, then the derivative of that, what happens is that 8 comes down the front, and then the power gets reduced by 1. So that's 8x to the power 7. So nice and simple. That applies for all real values of n. So I could have written up here that n is real. So for all real values of n, that works for. So it applies for negative numbers, applies for fractions, it even applies for square roots and irrational numbers and that sort of thing. As long as they're real, then that applies and that works. And that comes from the first principles of differentiation. So we're going to be having a look at that today and doing a few calculations using that. Okay, so speaking of which, let's have a look at an example. So if we need to differentiate this function here, so we're going to do it sort of one piece at a time, of course, and we're going to have a look at what happens. Okay, so let's have a look at this. So 3x squared. So what happens is that power 2 comes down the front, and there's already a 3 there, and so that gets multiplied. So any sort of number that's out the front of a function is always just stays there. That constant stays there and just gets multiplied through. So that'll be 2 times 3, so that'll become 6x. And 2 minus 1 is 1, so that just becomes 6x to the power 1. So that's the derivative of that first little bit there. Okay, and I've just noticed I'm just gonna back up here because I'm just gonna change this all into powers. So I'm just gonna rewrite f of x, okay? Because I've just noticed what the second term is. Having a look at that, I'm just gonna write them all as powers because if you've got anything with bottom line, so if I can rewrite 2 over x, I would write this as minus 2x to the minus 1. Okay, so just rewriting everything with powers, and then I'll leave everything else the same. Okay, now I can apply my power function derivation. So that 2 comes down for the front of the figure like we talked about before. So that will become 6x to the power 1. I'm just going to leave it as 6x. Now, this negative 1, I'll just draw something there. That negative 1 there. So that'll come down the front, right? So if that negative 1 comes down the front, it's negative 1 times by negative 2. So that will become positive 2x. And that negative 1 will go down by 1. So negative 1 minus 1 will be negative 2. Okay. Now, next bit, 7x. So that's effectively 7x to the power 1. So that 1 comes down the front. That just is 1 times 7. That stays as 7. So plus 7x. That 1 subtract y 1. 1 take away 1 is 0. So that's 7x to the power 0. And negative 3 constants always become 0. So all constants get, when you take the derivative of any constant, any number, again, decimal, fraction, square root, doesn't matter what it is, that always becomes 0. So that's all it is there. And so I'll just rewrite everything here. So that's 6x plus 2 over x squared. And I wrote this as x to the power 0 here. Remember, x to the power 0 is equal to 1, so that's just plus 7. So that's the derivative. We could have left this here as x to the power negative 2. We could have just left it as that. That would be perfectly fine, but I've just written it like that. So that's my derivative of that function. I hope that makes sense. Let's have a look at this next one. Differentiate y. And you'll see here in this first example, it was f of x. And so the notation is f dashed of x for the derivative. Here we've got y equals, and we're going to be using the different sort of notation. So we're going to use dy dx for our notation here. So let's do that now. Now, again, this is written in a different way. Okay, so we've got this like root x on the bottom, and so I'm just going to divide through by that root x to get it in a nicer sort of fraction. So I'm going to write this as 3x cubed over. Yeah, I'm going to rewrite root x as x to the power half, because we know that the square root of x, you can't rewrite that, and then minus 6x squared over x to the power half. So I've just divided through by that root x there. That's x to the power half. I've just divided each part by x to the power half. Okay, and so what that equals is that's equal to, and now we've got 3, and then remember, in our index laws, when we're dividing, then we subtract the powers. Okay, I'm going to do the same thing over here. When we're dividing, we subtract the powers. So that will be 3x, 3 take away half. Well, 3 take away half, so that's 6 over 2. 6 over 2 take away 1 over 2, so that's going to be 5 over 2. Okay, take away 6x, and then we've got 2 take away half, so that's 4 over 2 take away 1 over 2, so that's going to be 3 over 2. So now I've written it as powers. Life is a lot easier. Okay, so therefore the derivative of y with respect to x, or otherwise known as dy dx, is equal to, so that 5 on 2 comes down the front. I'm just going to take my time a little bit here. 5 over 2 comes down the front, and then we've still got the 3x, and then that 5 over 2, we subtract 1 from the 5 over 2. So 5 over 2 take away 1, otherwise known as 5 over 2 take away 2 over 2, is 3x, 3 over 2. And you'll get used to these ones, you do them all the time. Take away, that 3 over 2 comes down the front. And then we have 6x, it's a poor x, my apologies, 6x. 3 over 2 take away 2 over 2, because we're minusing 1, is equal to 1 over 2. Okay, so I've got that. And then we'll just simplify those fractions there. So 5 over 2 times 3. 5 times 3 is 15. So it's 15 over 2x to the 3 over 2. Take away 3 times 6 is 18 divided by 2. So that's just going to be 9. So 9x to the power half. And so that's my answer for the derivative of that second one. Hopefully that made all good sense. Let's have a look in the application. Let's actually find the gradient of a function here, okay? So we want to find the gradient of g of x is equal to 3 over x plus 2x when x is equal to 2. So remember, the derivative tells us the gradient at any point. So the first thing we need to do is find the derivative, and then we just need to substitute in x equals 2 into the derivative function, and that will tell us what the gradient is. Okay, so let's do that. Just going to firstly just rewrite g of x as powers. So that's going to be 3x to the negative 1, it's on the bottom line, plus 2x. And now I'm going to find the derivative. G dash of x is equal to, the negative 1 comes down the front, that becomes negative 3x. We subtract 1 from the power, so that becomes negative 2. And the derivative of 2x just becomes plus 2. Okay, so there's my derivative function. Now I want to substitute in there. So the gradient is going to be equal to g, that's a terrible g, overcompensated, I might do another massive g. So g dashed of 2, so we're going to substitute in the value of 2. That will tell us the gradient is equal to negative 3. I'm going to substitute into about negative 2 plus 2. And I'm just going to rewrite this and just have a little play around with this to see if this makes something better. So that would be negative 3. That 2 will put it onto the bottom line. So it's 2 squared plus 2. So it goes like that. So that's negative 3/4 plus 2. I'm just going to do plus 8 over 4 as for the plus 2, and so that'll be equal to negative 3 plus 8, so that'll be 5 over 4, and that is the gradient of the function when x is equal to 2. Okay, so that is the answer to that problem. Hope that one makes sense. Last question for this video. Find where this function has a gradient of negative 5. Okay, so again, the gradient comes from the derivative. And so we need to find the derivative, and we just solve where the derivative is equal to negative 5. Okay, so let's do it. Again, I'm going to rewrite the function so it's in powers with, written powers like this, x to the half, rather than having root x, because it's just hard to think about when it's written like that. So there's my rewritten function. Now, dy dx, my derivative of y with respect to x, is equal to, half comes down the front. So that's going to be negative 3 over 2, with the half coming down the front. X, and we subtract 1 from half, and we get negative half. And then derivative of negative 2x is just negative 2. Okay, so there is my derivative. Now, the gradient is equal to negative 5. Therefore, we know that negative 3 over 2x negative half minus 2 must be equal to negative 5. And this will tell us, we'll be able to use this to solve for x to be able to figure out where the gradient is equal to negative 5. Okay, so let's do just a bit of solving now. So this will be negative 3 over 2. I'm just going to rewrite that as 1 over square root of x. Okay, is equal to, I'm going to move that negative 2 to the other side, so I'm going to plus 2 to that, so it'll be negative 3. I'll leave that, I'll have 1 over root x on this side, and I'm going to, well, the negatives will disappear because we're going to negate that negative there and that negative, so we're just timesing both sides, so I'm not even going to worry about those. But we're going to times by 2, so 3 times 2 is 6. 6 divided by 3 is 2, so that's all going to be equal to 2 by multiplying by 2 over 3 effectively, or negative 2 over negative 3 if the negatives disappear. Okay, flip both upside down and we get root x is equal to half. And square both sides, we get x is equal to 1/4. Okay, so the x value, when x is equal to 1/4, we're going to get a gradient of -5. It just the question is a bit unclear. It says find where that has a gradient of 5, x is equal to 1/4. I could easily go and substitute that back into the original function to find the y value if the question asked for the coordinates. I'm just going to leave that for today's video because I think that's enough work for me today. Thank you. I'll see you in the next video.